In this video, we're going to take a look at the factors that alter the melting points of fatty acids and membrane fluidity. First, what we're going to see is that there is an inverse relationship between these two properties. So things that decrease our melting point of the fatty acid are going to be the same factors that increase membrane fluidity. And if we take a look at a couple simple fatty acids in the figure on the left-hand side, we'll take a look at what happens with unsaturation. So with our panel A, we have a saturated fatty acid. Note three-dimensionally that it does have a nice linear form to it. However, in panel B, you can see that the insertion of this cis double bond results in a kink in the three-dimensional structure of the fatty acid. And what that's going to result in is what we see in the bottom panel. Notice with our saturated fatty acids in panel C, those fatty acid tails are able to pack quite nicely together very tightly. And in contrast, when we have those double bonds, cis double bonds, as highlighted with the red coloring, those kinks result in some decreased ability of those tails to pack together, and that's going to translate into either a lower melting point if we're just talking about the chemical behavior, or an increase in the membrane fluidity if we're talking about a lipid bilayer. So if you were to have a fatty acid, compare fatty acids with the same overall length, same number of carbons in it, what you'd see is that a saturated fatty acid would have the highest melting point due to the ability of these hydrophobic tail groups to pack very nicely together with one another. And that would be followed by a trans unsaturated double bond. Those are less common. What we're more commonly going to see is the cis unsaturated double bonds. So those would have the lowest melting point or highest membrane fluidity. So we'll take a look at some of the other factors that can alter our melting point and membrane fluidity. Again, these are going to be, those two properties are going to be inversely related to one another. So having a shorter chain length is going to result in a lower melting point or an increased membrane fluidity. Having a branched chain fatty acid will also enhance the fluidity and lower our melting point. Those branched chain fatty acids aren't very common in humans, but some bacteria do have them. Our unsaturated fatty acids, saturated fatty acids have a lower amount of membrane fluidity or a higher melting point. Again, remember we're talking about how easy we can kind of pull apart these tails from one another, or how good the packing of them is. Our cis unsaturation, we said, will lower our melting point or increase our membrane fluidity. Polyunsaturation is going to have an even greater effect than just mono single cis unsaturated double bond, so that would enhance it even further. If we take a look at this table here, we'll try to highlight or point out these factors or features we were talking about. What we're going to do first is take a look at our saturated fatty acid, which has the structure I there. All we're doing here is varying the number of the methylene groups that are present in that fatty acid tail, the chain. And so as we increase our number of methylene units, I've put in parentheses the total number. So recall that 12-0 means we have 12 carbons in the chain. 0 means 0 double bonds. So looking at simply a saturated fatty acid, as we increase the length of that fatty acid chain, we're also seeing an increase in our melting point. So melting point is dependent on the length of the fatty acid. Remember, that would oppose your membrane fluidity. So lauric acid would have your highest degree of membrane fluidity. stearic acid would have the lowest membrane fluidity. If we take a look at the unsaturated fatty acids, what we see, now we're looking at structure 2. We have 3 different groups we're varying. The methylene Y, X, which is, this is going to control the number of double bonds. And notice they're all cis. And then W is just the methylene linker on the other side of the double bond. What we're going to pay attention to, we can see the first couple. Again, I've already gone ahead and told you how many total carbons are on the chain, so you don't have to add those up. But we see that the palmitoleic acid, which has just 16 carbons in it with 1 double bond, that has a lower overall melting point than oleic acid, which has the same number of cis double bonds, but has a longer structure, having 18 carbons. So what we'll do next is compare our next 3 structures. This makes the comparison a little easier because we're only varying the number of double bonds. We're not varying the length of these. What you can see is that if we keep the length, our number of carbons the same, and we increase our number of double bonds, you're seeing a decrease in the melting point with those increasing double bonds. So lowering the melting point, again, means increase in membrane fluidity. And then our last structure, the arachidonic acid, we're also seeing a low melting point where it has 4 double bonds. We've also changed there the number of total carbons. So putting this, trying to give you a visual for what this might look like if we compare 3 known natural fats, your olive oil, which is a liquid at room temperature, butter, which is a soft solid at room temperature, and beef fat, which is a hard solid at room temperature. What we're comparing, the green in the center represents the percent of the fatty acids that are unsaturated. Our other 2 colors, both the gray and the yellow, are saturated. The yellow represents the shorter fatty acids, the gray, the longer. What we notice first is that the liquid at room temperature has the highest amount of the unsaturated fats. And again, we said that cis unsaturation is going to enhance our fluidity or lower our melting point. And then if we compare our butter and our beef fat, what we're seeing here, they have a comparable amount of the unsaturated in green, but we're seeing a larger percentage of the shorter saturated fatty acids compared to the beef fat, which has a larger amount right here of this longer saturated fats. And we said the shorter chain has a lower melting point. So that's how we arrive at our olive oil being a liquid, the butter being a soft solid, and the beef being a hard solid. This just puts that table has more naturally occurring fats than just the 3 in the graph. And what you can see in general for the trend, the items at the top of the table, the food products at the top of the table, tend to be more solid fats at room temperature. The bottoms are our oil products. They're liquid at room temperature. And what you can see is that we're changing our percentage of saturated fatty acids. That's decreasing as we move down the table and become more liquid. And our amounts of the monounsaturated, polyunsaturated fats are both increasing as we move down the table. So those favor having the liquid products since those polyunsaturated, monounsaturated are going to lower our melting point. What we also see is that the fatty acid composition can be altered. In this case, we're looking at E. coli cells when they're grown at different temperatures. just pointing out, we said that this is looking at the different fatty acids in our E. coli growing at different temperatures. It has the shorthand nomenclature for the length and the number of double bonds. If we just simply want to see what's going on here or summarize what's going on here, if we take a look at the ratio of unsaturated to saturated fatty acids, what we can see is we have a higher percentage or ratio of the unsaturated fatty acids present at the lower temperatures. We have a higher amount of the saturated fatty acids present at the higher temperatures. So that goes along with our melting point, where the unsaturated fatty acids lower our melting point, and that's necessary so that the bacteria can maintain some type of fluidity at those lower temperatures. The last factor we looked at that could alter membrane fluidity was cholesterol. So cholesterol would have a similar effect as having a cis unsaturated double bond or having a branched chain fatty acid. The cholesterol is able to embed itself into the membrane using its polar hydroxy head group to interact with our phosphate head groups at the top. And then you can see that steroid, the hydrophobic steroid nucleus, is going to disrupt those lipid tails so they're not able to pack together as tightly. So cholesterol is going to increase, its presence will increase our membrane fluidity. All right, well, that's a wrap on that. Hope that was helpful.